The College of Dairy Science and Technology was established in the year 2008 with the undergraduate program of BTech Dairy Technology, a 4-year program. Now the college is offering undergraduate, postgraduate and the PhD programs in the dairy technology, dairy engineering, dairy chemistry, dairy microbiology and dairy economics and business management. The college is having 5 departments, of which dairy engineering is one of the major department with the mandate of development of technologies for the processing of milk right from the milk when it is at the dairy farm. The farmers oriented activities of the department have taken it to the reputation of a good department amongst the other dairy science colleges also. The department has transferred technologies of milk chilling and is working on the development of technology for mozzarella cheese making under a extramural project funded by the DST. The department is undertaking activities in the area of application of renewable energy such as solar energy and has developed a solar based milk sterilization technique. Through this informative video, the information on basic vapor compression refrigeration system, some of the definitions and some of the basic principles involved in basic compression refrigeration system will be elaborated. First of all, the refrigeration system means the removal of heat from a system to lower its temperature below that of ambient temperature. There are so many refrigeration techniques, but out of all these, the vapor compression refrigeration system is most widely used, whether it is home comfort or the industrial applications. Because of ease in operation and compactness, this system is highly useful and every person encounter it in its daily life, as we are using refrigerators at our homes, air conditioners at our homes, or while traveling in car we are enjoying the refrigeration or the cool environment. Basic principle of refrigeration system is that evaporation causes cooling. Here in this vapor compression refrigeration system, a medium that is called the refrigerant gets evaporated by absorbing its latent heat of evaporation in the evaporator. This heat is supplied by the space or the commodity to be cooled. One important definition which is related to the capacity of these refrigeration systems is the ton of refrigeration, or commonly known as TR of refrigeration system. 1 ton of refrigeration, it is the standard term used to rate the refrigeration systems and is defined as the amount of heat removed from 1000 kg water to the evaporator. As we can see in the diagram, 2 portions of different color have been shown, and these color markings. The vapor compression refrigeration system is a refrigeration system which is widely used for space heating, to chill the milk and to produce effect for the enhancement of shelf life of the various commodities. This refrigeration system consists of mainly 4 parts, that is evaporator, compressor, condenser and throttle or expansion valve. The evaporator is the part where the refrigeration effect is being produced with the heat exchange between the refrigerant and the commodity to be cooled. In the evaporator, the refrigerant is being converted from liquid to the vapor form, which are sucked by the compressor, and these vapors are raised from low pressure, low temperature to high pressure, high temperature, and these high pressure, high temperature vapors are then fed to the condenser, which is again a heat exchanger which exchange heat between the vapor refrigerant and the atmosphere, where the heat is being delivered or is being transferred so that the vapor refrigerant can be condensed back to liquid form, and this liquid refrigerant is again through receiver being sent to the expansion valve and then to the evaporator hence the cycle completes. The refrigeration system works between the two pressures, that is low pressure, which is evaporator side, and the high pressure, which is at the condenser side. Between these two pressures, these vapor compression refrigeration cycle works. The heat to be delivered or to be released out by the condenser consists of two components. One component is heat that is being taken by the refrigerant in the evaporator, and the second the heat which is added during the compression process, and this sum total heat has to be released out by the condenser. So the condenser must be designed in such a way that it should keep on transferring heat and whole of the refrigerant vapor should be converted into liquid form. The main aim as shown on this pH diagram is that we have to follow the liquid line to maximize the COP or maximum effect that we can get out of that particular designed refrigeration system. This refrigeration system, which consists of evaporator, compressor, condenser and the expansion valve, these components are designed in such a manner that design of one component depends upon the design of another component. So individually we cannot replace the component unless it is designed for that particular pressure. The compressor is known as the heart of the vapor compression refrigeration system. The refrigeration systems in milk industry or the dairy industry, these are used for cooling milk directly after it leaves the cow and before transport to the central creamery, and it is done by using the component that is called the BMC or the bulk milk chiller, keeping the raw milk cool after it enters the creamery. Again we are using the BMC, and these systems are used for ice bank systems in large dairy plants where milk is being chilled by heat exchange between the water and the milk, such as in case of PHE or plate heat exchangers. These systems are being employed for product storage areas such as cold storage, where the split type of systems are being used and the product is being stored. Since in dairy plants the temperature range varies considerably, that is for milk it is in the plus side and for the ice cream and butter it is in the minus temperatures or the sub-zero temperatures. As we can see, the diagram has been depicted in two color schemes, and these different colors is showing that the whole system operates between the two pressures, that is low pressure and the high pressure. The evaporator operates under low pressure, whereas from the compressor output to the condenser and up to the expansion valve, the whole system operates under the high pressure. The same thing has been shown in the side diagram, which shows low side and high side. In the evaporator, the heat exchange between the commodity to be cooled and the refrigerant is equal to the latent heat of vaporization of refrigerant, whereas the same heat is sensible heat for the commodity side. In the condenser, the heat or the latent heat of vaporization, which is equivalent to the latent heat of vaporization of refrigerant, and the heat added during the compression process has to be delivered to the outside environment or to the suitable cooling medium. The condenser is shedding this total heat, that is heat absorbed in the evaporator and the heat added during the compression process to the environment. Now the heat which is being added in the evaporator is lowering the temperature of the commodity, whereas the condenser, which is shedding heat to the environment, is adding heat to the environment basically. The evaporation process, as we know, is a isobaric or isothermal process. So that's why evaporator operates in a particular constant pressure conditions. Similarly, condensation is also a isothermal and isobaric process. So the condenser has to work under the constant pressure process. The compression process, which is considered to be an isentropic process, but in actual practice it is a polytropic process. Now we can see on the pH diagram or the pressure enthalpy diagram the schematic representation of evaporation, compression, condensation and the throttle process, which have been earlier depicted in a schematic diagram. On this pH diagram we can see the two curved lines. On the left hand side the line is known as liquid line, whereas the curved line on the right hand side is known as vapor line. It means if we follow the liquid line, the refrigerant will remain in liquid form, and as we move from left to right, that is from liquid line towards the vapor line, the two phases, that is liquid and the vapor phase, they coexist, and if we are more nearer to the liquid line, that implies the refrigerant is in liquid form, and if we are closer to the vapor line, it means refrigerant is in vapor form. Towards left of the liquid line, the region is called subcooled region, whereas the region which is right hand side to the vapor line is known as superheat region. On the pH diagram, the evaporation process is marked as a horizontal line parallel to the enthalpy axis, and this line lies between the liquid line and the vapor line, and in case of superheating of vapors, this line may extend towards the area of superheat, and this line on the diagram is shown from point 5 to 1, and from 1 to 2 the line shows the compression process, and it is clearly showing that the pressure of refrigerant vapors is being raised to a higher level, that is up to point 2. From point 2 to point 4, as we can see on the diagram, the portion 2 to 3 shows the removal of sensible heat only, whereas the portion that is 3 to 4, which is lying in between the vapor line and the liquid line, shows the removal of latent heat during the condensation process. The line from 4 to 5, it shows the passage of refrigerant through the expansion or throttle valve, and thus completing the refrigeration cycle, that is 5, 1, 2, 3, 4 and again 5. From this pH diagram we can clearly see the refrigerating effect and the amount of heat to be removed during the condensation process. Now this whole vapor compression refrigeration cycle or vapor compression refrigeration system, it indicates that refrigeration system is working as a heat pump, which is taking heat from the base or the commodity which is already at lower temperature, and then throwing the heat to the area or the environment which is already at higher temperature. So thermodynamically speaking, the heat is being extracted from the sink through a refrigeration system, and then heat is being thrown to the source which is already at high temperature. And we can also see that these refrigeration systems always work between the sink and source temperature. So lower the sink temperature means more is the refrigeration effect, and again if we see that heat has to be delivered to the source. And from the pH diagram we can also see that for a given system, if the difference between the low pressure and high pressure is lesser, the system will be more efficient. There is a term that is called coefficient of performance or COP, which is a measure of efficiency of the refrigeration system, is defined as the ratio of refrigeration effect produced to the heat input. So higher the refrigeration effect and lower the energy input, COP will be higher. So the whole effort while designing the basic refrigeration systems is to get as large as possible the refrigeration effect and with the as little as possible input energy during the compression process. The various possible refrigeration cycles on the pH plot can be shown. As we can see in this diagram, the compression process and the evaporation process, that is point 1 and point 2, they lie between the liquid line and the vapor line. Therefore, such type of processes are called wet compression process. Similarly, we can see on another diagram that the point 1, that is the end of evaporation, is still between the liquid and vapor line, but at the end of compression the point 2 lies on the vapor line. Therefore, this process is called dry compression process. The superheated compression process can be shown as in the given diagram. In this case, we can see that the compression point, that is point 2, has been extended in the superheated region. So such a process is called superheated compression. The vapor is dry at the end of suction. The process can be shown as given in the diagram, and we can see at the end of the evaporation the point 1 lies on the vapor line, and at the end of compression the point lies in the superheated region. Similarly, when the vapors are superheated at the end of evaporation, it can be shown in the plot. Another plot which is showing that vapor is superheated at the suction of compressor and liquid is subcooled before throttling. So these are the 6 possible compression cycles depending upon the condition of the refrigerant at the end of evaporation as well as at the end of compression process. The medium which is being circulated in the vapor compression refrigeration system is known as refrigerant. The refrigerants should be stable, they should be non-toxic, they should be non-reactive with the material being used for the construction of the components. They must have sufficient high latent heat of evaporation so that refrigeration effect can be maximized. Refrigeration or refrigerants can be a primary refrigerant or it can be a secondary refrigerant. The primary refrigerants, they extract the heat in the evaporator and cool the environment, whereas the second refrigerant, they are firstly being cooled by the primary refrigerants and then used to lower the temperature of the commodity or the space. Now we'll go for classification of refrigerants. The refrigerants are usually classified as on the basis of working principle. They are primary refrigerants, and these are the heat carrier substances that take part directly in the refrigeration system and cool the space by absorption of latent heat. And second is secondary refrigerants. These are the heat carrier substances that are first cooled by primary refrigerants and are subsequently used as a medium for producing cooling effect in the product or the space being refrigerated. The primary and secondary refrigerants are shown in the given table, and the parameters for comparison of these refrigerants are cyclic or non-cyclic operation. So we can see that primary refrigerants operate in a cycle, alternatively evaporating and condensing, and secondary refrigerant are non-cyclic operation and no phase change is there. And next parameter is heat absorption, that is latent heat and sensible heat. Then refrigerating effect. In case of primary refrigerant, this is higher than the secondary refrigerant, and cost wise primary refrigerants are expensive as compared to the secondary refrigerants. The primary refrigerant quantity required is less than the secondary refrigerants, and similarly the primary refrigerants, depending upon its properties, may or may not corrode the metal in which they are coming in contact, whereas secondary refrigerant, they are usually corrosive in nature. Primary refrigerants, they don't require any antifreeze, whereas the secondary refrigerants, they require some antifreeze for efficient working. So common examples for primary refrigerants are R11, ammonia and SO2, whereas secondary refrigerant examples include water and brines. Chemical composition wise, the refrigerants can be generically classified as halocarbons, isotrope hydrocarbons and inorganic refrigerants. On the basis of nature of refrigerants, these can be natural refrigerants which exist in nature such as water and non-flammable, and the artificial refrigerants which are man-made and are synthetically produced such as isotopes and halocarbons refrigerants. Safety wise, safe refrigerants which are non-toxic and non-flammable, for example carbon dioxide, water and freon family refrigerants, and toxic refrigerants which have irritating or obnoxious smell and are harmful. They include sulfur dioxide and ammonia, and flammable refrigerants which are strongly prone to catch fire are butane and isopropane, etc. The commonly used refrigerants under halocarbon compounds, the first one is R11 or trichloromonofluoromethane. So application wise, these can be applied for air conditioning of office buildings, theaters and departmental stores, flushing agents for cleaning the internal parts of the compressors during the overhauling, and flushing out moisture from the systems. Next refrigerant in this category is R12, that is difluoromethane, that is CCl2F2. Application of R12 includes as most widely used and popular refrigerant of freon group, equally suitable for low, medium and high temperature applications, used in domestic refrigerators, freezers, water coolers, etc., and universally used in sealed type compressors because of being excellent insulators. The next category of refrigerants are isotrope refrigerants, that include R500, which is a mixture of 73.8% of R12 and 26.2% of R152, and it is non-flammable, non-corrosive and low in toxicity, fairly high solubility with oil. Solubility with water is critical. Moisture needs to be kept out of the system by careful dehydration and by using dryers. For the same motor size and when used for the same purpose, the refrigeration capacity with R500 is about 20% greater than that with the R12. Leaks detected by using soap solutions, halide torch or electronic leak detector. This refrigerant is used both for commercial and industrial applications, but only with reciprocating compressor systems. Next is in isotrope refrigerant is R502. It is an azeotropic mixture of 48.8% of R22 and 51.2% of R15, and these are non-flammable, non-corrosive and practically non-toxic. Good refrigerant for obtaining low and medium temperatures, positive evaporator pressure at low temperature, lubrication of oil retains its viscosity at low temperature, and that ensures better lubrication, less compressor displacement, and low power input for these refrigerants. This refrigerant has replaced R22 because of difficulties of high discharge temperature and poor oil return experienced with R22. The blend R502 has become the standard refrigerant for frozen food lockers, frozen food processing plants, frozen food display cases, and in storage units for frozen foods and ice creams. Under the inorganic refrigerants, ammonia is widely used and it is written as R717 or R717. It is excellent thermal properties, high latent heat and high heat transfer coefficients, large refrigerating effects with relatively small size machinery, lighter than oil, and can be easily separated. However, in the presence of moisture, ammonia forms an emulsion with oil and that creates certain operating difficulties. Low specific volume and low volumetric displacement, low mass of liquid to be circulated per ton of refrigeration, cheap refrigerant, and low running cost, leaks easily detectable due to pungent odor. The leak is detected by bringing a sulfur candle near the leak. Dense white smoke is given off when ammonia vapor is present. Highly volatile and explosive when in contact with air. It's toxic, irritating to eyes, nose and throat. It's non-corrosive to ferrous metals but attacks copper and its alloys such as brass and bronze. Ammonia is an ideal refrigerant and is invariably used in ice factories, breweries, and cold storage plants. Next in this category is water, that is H2O, and is coded as R118. It is non-toxic, non-flammable, thermally stable, and chemically inert even at high temperatures. Very high enthalpy of vaporization, very safe refrigerant, no leakage problem on health or environment. High level transfer coefficient allows small dimensions for condenser and evaporators. It's available in abundance at no cost. Light system components due to very low operating pressures with water. So water is essentially used as ice to produce the cooling effect. Its high freezing point limits its use in vapor compression system. Water is used as a solvent in vapor absorption system and also in steam jet refrigeration system. Now I would like to compare Freon versus ammonia. So Freon R12 is superseding NH3 in domestic and commercial plants because of its low toxicity, completely safe refrigerant as it does not affect the food products and is also non-irritant to human body. Home window air conditioners, package units, small central air conditioners also use F12 as refrigerant. Being an excellent insulator, it is universally employed in sealed compressor units. Before the advent of Freon refrigerant, ammonia has been used universally for many applications due to low running cost, easy maintenance, low volumetric displacement, low weight of liquid refrigerant per ton of refrigeration, etc. Even today, ammonia is used in cold storages, ice manufacturing plants, skating rinks, and breweries without exception. Since Freon 12 is associated with ozone depletion. Its production and use will be completely phased out in the coming years, with its replacement being both costly and time consuming. Ammonia will remain evergreen and popular due to its ozone depletion potential and global warming potential being practically zero. As we can see, in case of phase changing materials or PCM based refrigeration systems, first the primary refrigerant lower down or change the phase of the material, and then that material with the change phase, that is most of the time that is the solid phase, is used to give chilling effect to the commodity or the space to be cooled. The application part of the refrigeration system, particularly in dairy sector for handling of milk right from the farm to the milk processing units, is of immense importance, as it provides or helps in extending the shelf life of raw milk from few hours to the few days. Also, such type of refrigeration systems are used during the processing of milk in milk plants. The secondary refrigerants are being circulated, whereas the vapor compression systems are used to lower the temperature of water or brine solutions or the glycol based solutions. The most important application is in the plate heat exchangers or the PHEs, which are being used for the pasteurization of the milk. The pasteurizers consist of heating sections, regeneration section and the chilling section, as we have to cool the milk immediately after achieving the required heating temperature or the required pasteurization temperature of minimum 72 degrees centigrade, and chilled to the temperature may be as low as 2 degrees centigrade, or chilled using the primary refrigerants. Another application part of these vapor compression refrigeration system is where we are storing the product, that is the product storage or cold storage areas. Since the liquid milk is being stored at a temperature above zero, that is around 4 to 5 degrees centigrade, and the products such as ice cream or the butter has to be stored under the sub-zero temperatures. So these vapor compression refrigeration systems are capable of achieving these two requirements in the milk plants. The most important equipment which is being used for chilling of milk or extension of shelf life of milk from the farm itself is called bulk milk chiller or BMC in short. BMC or the bulk milk chiller, it is a container as we can see, but it is having a vapor compression refrigeration system which chills the milk to the required temperature of 4 degrees centigrade. The BMC consists of a cavity which is made of stainless steel, having the evaporator coil suitably placed so that milk can be chilled in the required time duration, that is of 2 to 3 hours after the milk is received from the dairy farm. The BMC is having essential components like agitators, which are basically helping to eliminate the chances of cream layer separation. The BMCs should be capable of producing the required chilling effect as per the food safety and standards law, that is of 4 degrees centigrade. BMCs can be placed on the farm itself, or these can be placed at some another point where the milk is being collected, or for small milk plants, BMC is the first point where milk is being received. The advantage of using such chilling system is that the processor gets sufficient time to process the milk into various milk products. Since BMC is a very important component in the whole milk supply chain. So the Department of Dairy Engineering is doing research work so that the farmers, the vendors and the consumers can be benefited and the incidences of milk adulterations can be lowered down. So one such effort was fruitful and the technology was developed, and this technology is known as PCM based GADVASU milk chiller. In this milk chilling system, a phase changing material based component was introduced in which the primary refrigerant first convert the phase changing material to the solid phase, and without coming in contact with the milk, this phase changing material chill the milk in the required time of milk chilling, that is 2 to 3 hours. The advantage of using secondary refrigerants or PCM based refrigeration system is that we can lower down the capacity of the primary refrigeration system by almost half. Another advantage is that most of the villages, they don't have 24 hours power supply, hence it is very much required that at the time of milking, whether it is in the morning or in the evening, the power supply must be there to run the conventional bulk milk chillers. But with the use of secondary refrigerants or PCM based systems, this requirement of having electricity supply at the time of milking was eliminated, and also the use of generators in the absence of electricity has been eliminated. So the application of PCM based refrigerants for the milk chilling is of utmost importance in the countries where there is no power surplus. So towards the end of this video, I would like to sum up the whole content that we have learned during this presentation. The most important thing to remember is that the vapor compression refrigeration system is a cyclic system which consists of 4 components wise: evaporator, compressor, condenser and the expansion valve or the throttle valve. These components, when placed in a particular fashion, produces the refrigeration effect, which is a required not only for our home comforts or the industrial things, but to enhance the shelf life of highly perishable commodities like milk. We have learned that the whole system works between the 2 pressures, that is low pressure and high pressure, and we have also seen that if the level of these pressures or the difference between the pressures low side and high side is lesser, more will be the coefficient of performance of the refrigeration system. That is, with lesser input we will get more of the refrigeration effect output. Thermodynamically speaking, evaporation is a isobaric process. Condenser side condensation is isobaric process. Compression, theoretically we consider it as isentropic process, whereas practically it is a polytropic process. Expansion valve, the purpose is to transfer refrigerant from high pressure to low pressure side, but without losing the enthalpy of the refrigerant. Another thing that is more important, that is effort should be made that whole of the refrigerant should be in liquid form while it is entering into the evaporator, and it should be in the vapor form when it is leaving the evaporator. So by doing this, maximum refrigeration effect can be achieved with the same compression system and with the same condenser system. These type of refrigeration systems have wide application, as I have already told during the video that these refrigeration systems in the milk industry can be used to enhance the shelf life of raw milk, can be used in the PHE or the plate heat exchangers or pasteurizers. These have applications in the product storage, and even it has application during the supply chain of the milk products also.